Get started. Thank you all for coming to the IDSS Distinguished Speaker Seminar. I am very, very pleased to introduce Professor Arun Majumdar as our speaker. I've known Arun, I think, for over 25 years now, since he was a professor at UCSB and then later as he moved to Berkeley. He's worked on very innovative research in nanoscale material and devices for plenty of different kinds of applications. And more recently, he's been also working on electrochemical devices for storage, generation, refrigeration, and so forth for energy applications. He's been doing amazingly interesting work on the power grid and the connection between data and markets and the innovation that we're going to hear a lot more about today. But Arun has done a lot of other interesting stuff, and in particular, he has spent a good part of his career on his service to the United States as he was the founding director of ARPA-E. ARPA-E is the Advanced Research Projects Agency for Energy, and he was appointed by President Obama. I've actually attended a lot of talks that Arun gave at the time when he was running ARPA-E, and I thought it was really amazing about the sort of the structure and the organization that you put together in that. And I understand that the agency had bipartisan support, which seems to be miraculous given the way our country operates these days. He's also served as an acting deputy director, the Secretary of Energy, if I'm not mistaken, right? And so he's been very much involved with the government, with policy making, still is on the advisory board, I think the co-chair of the advisory board for the Secretary of Energy, and I think that his connection to the government and Washington and his research that he's doing at Stanford and before that actually at Google and then Berkeley puts him in this ideal sweet spot that I always talk about at IDSS of being able to think about the societal challenge from all dimensions, but also be able to impact the policy in these areas. So we're very excited about Arun's talk and we look forward to it.
Well, Munzer, thank you very much for the invitation and congratulations on putting this very interesting, institute, I think, right? Institute for on data, because I think this is one of the revolutions that is happening right now, and it's sometimes hard to know whether you're part of something big when you're in it. But I think what I've heard of stepping back and looking at the connection between data and a wide variety of things is right on the mark. So congratulations on that. It's always nice to come back to MIT and give a talk, and I'm told that today is a holiday for students, and despite that, you're all here. I'm honored. But let me just say, before I start my talk, there's a very important point. When you hear a talk about the grid, and it's given by the electricity grid, and it's given by a mechanical engineer, there are 2 points to note. And I go back to the words of our famous President Ronald Reagan, trust but verify. So very important. And the other point to note is that this will be simple, because that's how I understand the electricity grid, coming from a completely different background to understand. The only way I can understand is simplify it. I hope I don't oversimplify. But what I'm going to talk about are some issues that the grid is facing. Not too many solutions, frankly, but some of the issues that the grid is facing, not just in the United States, but worldwide. And what I'll tell you about is something that some of the work that we're doing at Stanford, and it is, I believe, just the start of something, hopefully, that can grow into something useful. So when I talk about the grid, this is, as the US National Academy of Engineering has said, this is the greatest engineering achievement of the 20th century. And it started in the United States, going back to Tesla and Edison in the 1890s. And this grew all over the world and has essentially changed the way we live, because without the grid, it's hard to go back. But I also want to place on this, this is the proxy for economic development, as you can imagine. And I want to overlay on top of this where the people are. And what you find is that they don't coincide. The United States, of course, we have 300 million people, and it is well lit and is economically developed, the most developed nation. But there are many parts of the world where people have not yet turned on the lights. And there are about 1.5 billion people out of the 7+ billion people who don't have access to the electricity grid. And there are about another 1.5 billion people who do have access to the wires, but there's not much power flowing. And so roughly half the world's population do not have access to the grid. So we are, of course, very fortunate. But whether today's grid will go and be connected to them, or whether there's other ways or architectures that can be used, is a question that a lot of people are asking right now. And I think there are opportunities where this grid that I'm going to talk about is not the right model. And in fact, much of my work at Google was to look at other architectures that may be better suited for where the grid does not exist today. But I'm not going to talk about that. Maybe we can get into it in a Q&A session if necessary. So this is a global challenge. And if there's a problem that you can find that is this big, it's very hard to find problems as big as this. So let me go back in history and talk about the Tesla-Edison paradigm for the grid. The architecture of the grid has not changed since Tesla and Edison. The architecture. People say it's still the same grid. That's not quite true. Today, there are many more modern devices out there. But the architecture, how it is structured, and the paradigm that we live in has not really changed, although the devices are new. What is the architecture? Is that you have a centralized generation of large thermal power plants. And the reason they were large thermal is because it was cheaper per unit of electricity. And the cost came down with larger size. So that's why you find gigawatt scale coal-fired power plants, because they became cheaper as they became bigger. So you have large power plants, then long-distance high-voltage transmission lines to take the electricity from where it's generated to where it is used. And in the United States, that transmission lines, as you will see, is like a mesh network. And in fact, the electricity flows like water flowing down a hill. It can go anywhere. There are no routers today. And then you get to a local region where you have these substations that you may have seen, that you step down the voltage into distribution networks that are typically around 13 kilovolts or so along your neighborhood. And then you have step-down transformers out there. You get 240 volts, out of which you get, from the neutral, you get 120, and that's what you use. And the whole grid operates at 60 hertz. So this is how, and I'm just giving you something very simple. And there is a one-way power flow between the generation to the grid, and the generation always tracked the load. And the loads were passive, so you can turn on the light or your motor, and somewhere back in the generation, they knew that someone has turned on the load, so they would ramp up the generation. And we're going back in history now. The only way to communicate at that time was frequency. So frequency was a proxy for imbalance between the generation and the load. So if anyone saw that, hey, 60 hertz went to 59.9, they would ramp up the generation. And it's a very simple control loop to bring it back. And that's how the grid operated, and it had to be balanced in real time, because there's essentially no storage except for the inertia of this turbo machinery, which gave you a sort of room of about 8 seconds or so. And that was the only freedom you had in the system. And so the generation always tracked the load, so it's continuous, and there's one-way power flow. Now, based on this architecture, we have created institutions around it. And in fact, what we have done is that we separated our generation in terms of the jurisdictionally. We've separated our generation to a wholesale market, which is where the transmission network is, a wholesale market. And then you have retail market where the distributed loads are. And this is purely a human construct. It doesn't have to follow the laws of physics. The electricity, the Kirchhoff's law, have to satisfy the laws of physics. But this is a purely human construct. So this is the sort of the jurisdiction-wise. So if you look at this, this is the transmission network. I mean, you can go to the internet and find these pictures. This is the transmission network in the United States at different voltage level. In the United States, we go up to 765 kilovolts, which is the highest voltage we have used. In China right now, they are testing 1.1 megavolt state grid, if you go to their center, which is the highest voltage that is practically being used. And they're now planning to 1.4 megavolts. And as you know, as the higher voltage you go, the lower losses you have if you want to go long distance. So China is sort of the bleeding edge in terms of high voltage AC and DC transmission in the world right now. So how does it actually work? In the United States, in the wholesale market, you can get solar plants or wind plants or utilities. I'm showing California utilities, where they can sell directly to the wholesale market and buy. These solar plants can go through a utility into the wholesale market. And the grid operator, whose job is to balance the grid and create this market for an exchange to meet the supply and demand, is in this case California Independent System Operator, or CAL-ISO, as we call it. And they actually run a market, so the price fluctuates just like any market. It's not exactly like the stock market, as I will show. And then, of course, these utilities have jurisdictional domain in California where they are a regulated monopoly. So where we live in the Bay Area, PG&E is the utility. If you go to Sacramento, it is SMUT, Sacramento Municipal Organization out there. And what they do is that their job is to distribute the electricity to your homes, to your buildings, to your factories, et cetera. And this is the retail side. And they are within the state. And this can go beyond the state. And in fact, that's why they come under federal rules. FERC is the Federal Energy Regulatory Commission, which sits in Washington, D.C. And they provide the rulings and the regulatory framework for the wholesale market to operate, because they can go beyond the state boundaries. These are regulated monopolies. There's no other electricity firm that can sell electricity to us in the Bay Area. And so that is regulated by the California Public Utility Commission, who decides the pricing for what we pay. And that pricing today in California is based on what are called tier structures. And the tier rates is that within a month, I start off with 13 cents a kilowatt hour. In tier 2, I go to 15 cents a kilowatt hour. And if I cross a certain kilowatt hours, I jump to 32 cents. And I don't even know when that happens. Most people don't know when they jump from tier 2 to tier 3. And this is why the rooftop solar is really helping, because they can keep them at tier 2, because at 32 cents a kilowatt hour, rooftop solar makes a lot of sense. So this is the way it is structured. And these tier structure, the actual numbers, are determined by the Utility Commission through a lot of calculations and all, in order to make sure that the wholesale price is lower than the retail price. Because these utilities are buying electricity from there and selling it out here. They're buying low and selling high. If somehow the wholesale price or the retail price becomes lower than the wholesale price goes above the retail, they go out of business. Can that ever happen? You bet it can happen. This is almost what happened in California in the energy crisis, when there was a little bit of gaming in the wholesale market and the prices were jacked up. So that happens once in a while. But I'm just explaining, in addition to the architecture and all, there are some jurisdictional issues that are very important for the grid. If you are to solve a problem, you got to do it in the context of what is there. So how does the system operator work? This is, in fact, a picture from a system operator. This is CAL-ISO. It's probably very hard to see. There's a big LED display out there showing the frequency, 59.995. And that's what they monitor all the time. And there are many time scales that they have that are involved. 60 hertz is 16 milliseconds, and faults happen often shorter than that. Then there are, long-term is asset planning. Over 10 years, you got to be able to plan your assets and make sure that your capital, that the outlay for what you plan for, it makes a huge difference on how much capital you want to raise, what kind of balance sheet you have. From the business perspective, this is very, very important out here. In between are the markets that the wholesale run. Most of it, as you'll see, day ahead, hour ahead, 5 minute. So it's not really like a live market. So let me show you how it works. So the first step is, this is the main grid. I show a little bit of storage, but there is really none. And the most important thing is to forecast the load. Remember, the loads were inflexible. You could turn on anything, and someone had to provide you electricity. So it's very important to forecast the load. And the load is forecast a day ahead. And it's done by history and weather and a combination of that. And then the day ahead, you essentially decide, you have a market clearing. Someone makes a bid in terms of how many megawatts they can produce, they can provide at so many dollars per megawatt hour. And then there's a whole bidding process and this clearing that happens the day ahead till the supply meets the demand. And the demand is forecast the day before. But then they don't quite get it right when you're actually running it. And so then there's a correction factor, which is the hour ahead market. And that also doesn't quite get it right when it comes to 5 minutes. So sometimes there's a 5-minute market, and then there's a frequency regulation market, which is really short term. So but most of the dispatch happens in the 90% of it in the day ahead. So this is like, you're balancing the grid. You have to do it in real time. There's no storage. So you have a big knob, then there's a smaller knob, and the smaller knob, and eventually you get it right because you're trying to satisfy the laws of physics through the market mechanism. That's what's going on out here. More recently, we have started doing what is called demand response, which is trying to control the demand. And that's very recent, and most of it is in shaving off peaks. So this summer, I'm told, it was extremely hot out here. And when it's hot, your air conditions turn on, and there's a huge peak. And instead of having a few plants that provide the electricity only for a few hours in a year, which is very expensive, why not just cut the demand a little bit and thereby make it much more economical to do so. So this is how the system works. This is a typical day in California. I just picked up a day, April 27th. And as you can see, this is the actual line. In fact, I have an app on I'm a geek of electricity, so I have an app of Cal ISO which tells me exactly what's going on. And I'm sure in New England ISO there are apps that you can get that you can see if you're interested. So you can see this is the day-ahead forecast. This is the actual demand, and there's a mismatch in California that's often about a gigawatt or a couple of gigawatts. And then there's an hour-ahead demand forecast, and then there's a 5-minute demand forecast. And you can get all this data available on the website. But this is just to show. It's very interesting, actually, that the demand increases and then flattens out, and then it increases again. Can anyone guess why that is so? Why does it flatten off in the middle of the day? I thought it was getting hot. This is when the solar hits the thing, and then you have what is called negative generation, and this sort of flattens up. And then when the sun goes down and people go home, there's a big ramp that comes up. And this is one of the biggest challenges that the California grid operator has to face. Oh, by the way, this is the capacity that is made available in case you need it. And this is, you got to think about this. They are being paid to provide a capacity, and you can see what the difference in the generation capacity that is kept just there in case you have an emergency, suddenly the load goes up, and that capacity is kept out there. And you can see this is not the most economical and affordable way to run a business. But that is what is available. That is what is done today. And this is not just in California and other places as well. So what is going on in the grid? There are two big drivers of change that are coming. One is a deep decarbonization of the electricity system. If you are to meet any Paris agreements and all that, if the grid is not decarbonized, there's no chance we're going to do that. So how can we decarbonize the electricity system? And there are various options. One is you can have deep renewable penetration, more than 50%. California has a mandate that by 2030 will be more than 50% renewables. And this is wholesale. This is not even the rooftop. It doesn't even count the rooftop. This is the wholesale. So that's one option. Then there's a demand-side management, which is basically saying that let's control the demand so that you don't have to put carbon-based electricity onto the grid. That's another option. The third option is carbon capture and sequestration. So if you have a lot of coal-fired power plants or natural gas power plants, you just capture the carbon dioxide of the plants and sequester and store it somewhere else. And you can decarbonize that way. All of them cost money. And finally, you have nuclear energy, and you can ramp up nuclear and because it's a carbon-free source of electricity. So these are the options. And so that's one trend that is going on. And there are not only just policies that have been made, this is not just the United States, this is worldwide. The second one is the increasing penetration of distributed energy resources at the grid edge. And this I'll talk a little bit about, and this has to do with consumer choice and a variety of other things, a little to do with policy as well. But on the first one, we are trying to decarbonize in a market, in a wholesale market mechanism, and here's the handicap we have, with no price on carbon. And this is the dilemma that a lot of the grid operators are facing. They deal with markets, but there's no price, but yet they have to decarbonize. So how do they do that? This is a big dilemma that the whole industry is facing today right now. So let me talk about the deep decarbonization. This is what is going on in terms of price of electricity that are being sold on the market from wind and solar. Talk about 50% renewable. Well, it has to play in the market, so the price is very important. This is the data on contract price. That is the price that have been long-term contracts that have been signed between a wind plant or a wind farm and a developer of a wind farm and a utility. And the utility will then use it or sell it, et cetera. And so it's not the cost. The cost is even lower than that. This is the price. So this is the actual data. I've just beautified it with some cosmetic colors and all that, but this is the actual data. And this blurring is the error bar in that. So you can see that the wind just went up a little bit, but right now, it is at about $30 a megawatt hour or 3 cents a kilowatt hour. In the United States, there's a tax credit. There's a little bit of incentive. And it's about 2.3 cents a kilowatt hour or $23 a megawatt hour. And so this is with that incentive on it. Solar has a 30% investment tax credit, and solar is coming down. This is silicon, polysilicon, and single crystal, as well as polysilicon and cadmium telluride mostly. And so this is coming down. It's about $40 a megawatt hour. So this is the lowest contract price that have been signed. In fact, $38 a megawatt hour on plants. And you're going to hit the $20 a megawatt hour pretty soon. I put this line out here. This has nothing to do with the grid. This is very important because at that price, you need that kind of a price for desalination, which is another use of electricity, for turning CO2 into a fuel, and the fuel is the best battery you can think of in terms of energy density. And you need to have carbon-free electricity or energy to be able to do that. And that's the price you really need for other applications that may show up once you bring down the price of carbon-free electricity. And this is, by the way, the first time in history where carbon-free energy is so cheap. And how cheap is that? By the way, this is now the unsubsidized, these are the world records. This is unsubsidized price in Morocco, 3 cents a kilowatt hour, or $30 a megawatt hour, unsubsidized. This is the best of class. And this is solar plants in Mexico, in just south of the border, is $36 a megawatt hour, or 3.6 cents a kilowatt hour, unsubsidized. This is amazing price. And by the way, as you know, in silicon, there's still some headroom to bring the photovoltaic cost, in terms of efficiency, to bring the photovoltaic cost come down. This is polysilicon, so there's still room out here. So these are going to come down, and in relative to others, here's where we are. This is US natural gas and China coal. And this is US coal and nuclear. And so you can see right away that the price of electricity from wind and solar are either the cheapest or going to be the cheapest pretty soon. And because the wholesale market is run based on marginal cost, the variable cost, okay, it's not the total cost, it's the marginal cost on a daily basis. And the marginal cost depends on fuel, right? So a natural gas plant or a coal-fired power plant has to use the cost of the fuel that is being used and then bid in the wholesale market. But solar and wind has no fuel. So the marginal cost is extremely low. And so it gets bid first and it gets adopted by the market. So this is a great business to be in right now. It is scaling in this is the gigawatt scale scaling that is going on around the world. So this is the scenario in terms of why the market, why that 50% renewable, while it was a mandate, actually thinks that it may be feasible even without the mandate. These are the other consumer demand side trends that are going on. Here are the cost of batteries, battery pack, and it's very faint out here. This is about $300 a kilowatt hour of a battery pack. And it is expected that the cost, this is lithium-ion batteries, there's still plenty of room in lithium-ion batteries itself. And that in terms of materials as well as the packaging, the innovations that are going on, and it's likely it'll come down to about $150 a kilowatt hour for battery pack in the next decade or so. And if that happens, the range and cost of electric vehicles are going to be comparable to the gasoline-based one without subsidies. And then you have, you will then, when this price comes down, you will have this exponential S-curve sort of increase in electric vehicles. This is in the United States and other parts of the world, this is already happening in a major way. And of course, these electric vehicles are, as you are now realizing, that these are not just connected for the electricity grid, they are connected to the computing grid. These are all connected. And you know exactly what's going on in the car, and when they're hooked up, you know how much power is going in. You can control the power flow if you want to. And so this is on the demand side. It's this is going on primarily driven by the cost of the batteries coming down. LEDs, this is what is called the heights curve. This is LED in terms of dollars per lumen coming down. And this is CFL, and this is where we are right now in terms of LEDs. This is incandescent. And if it's comparable, people are switching to this, and these are going to be networked as well. This is GE is making these with little communication chips in there to be networked. And so which means that you can monitor, you can control, you can aggregate all kinds of things. Thermostat, this is already happening, as you know. These are learning thermostats. And well, the learning could be a little better. I have a thermostat that I have to manually control, but nevertheless, it can change the setting, the data. It's controlling a big load. Number one, the data is being collected in the thermostat cloud, in this case Nest Cloud, as well as that cloud can be used to turn the thermostat a little bit to be able to turn off the air conditioner, turn it on when you need to, and so this is already essentially this is a beautiful looking switch. But the switch can be controlled remotely. And finally, as you know, this is going on in many parts of the country. This is rooftop solar, and I hope like the thermoelectric work that's going on out here leads to something which is like a combined heat and power, where you have a gas utility coming which is used for heating hot water, and if you place a chip out there, thermoelectric chip, you can produce electricity as well behind the meter. This is something that came out of our lab in Berkeley, Alphabet Energy, which is trying to generate power from waste heat as well. These are all the things that are happening, but all of them will be connected. So if you look at all the trends going on, if I were to summarize on the whole system, this is what is going on. You have today thermal power plants generating, and they put the electricity in the transmission line. Then it goes to the substation, the distribution network, and there's the customer out here. And there's a wholesale market that is run on the wholesale side out here. But there is a meter at every home, and as you will see, so this part is the grid system operator, which is managed by federal regulations. They have to follow federal regulations. I'm just repeating what I said. This is the retail side, which is then have to follow Public Utility Commission's ruling, and these are the tier rates that I talked about earlier. But their jurisdiction stops at the meter. They don't go on the other side of the meter, because the other side of the meter is my home. I can do anything I want. but they still have to maintain reliability of the electricity along a feeder line. And now what we're doing to this is trying to inject more than 50% renewables onto this grid, and the grid was never designed for it. They were designed for slowly moving generation that tracks the load. And I'm putting this behind the meter, which are large loads that are connected to the PV. It has its own, so Tesla has its own cloud, Nissan will have its own cloud. And the rooftop solar, whether it's Solar City or Vivint or others, they will have their own private cloud. And of course, thermostats will have their own cloud, whether it's Nest or Honeywell or Ecobee, they'll have their own data collection. And this is all going on in this unregulated part, which is behind the meter. And guess what? Not only can they monitor and control the power going into your home, which then the power is delivered by the utility, so that now they can control the power that the utility has to give you. This cloud can be used to aggregate these loads and generation across thousands and millions of homes, aggregate that load, and be dispatched into the wholesale market behind the utility. Okay? So now you see that this is a complex system now, which has technical issues. There's data, of course. There is jurisdictional, and there's bypassing that can easily happen. It hasn't quite happened yet. That can easily happen in the future. That's the world we're entering. And of course, it affects not only the jurisdictional issues, the business model, because now these people control. Imagine if there's a very lucrative market in the wholesale, and they want to sell their services of load or generation onto that market, and that destabilizes this grid. Who's going to pay the penalty for that? Is the utility. So utility is not very happy with that. So this is not only a jurisdictional, these lead to political fights as well. And it can be pretty messy. So when you do this, here's what, since the grid was really not designed for 50% renewables and large amount of distributed energy resource, which induce backflow of electricity, which grid was never designed for, you have lots of issues. Lots of questions have to be answered. Stability against intermittency, against big ramps, as well as backflow, cost, reliability, energy efficiency, emission goals. We saw in Germany that the emissions actually went up when they tried to integrate renewables because they decided to stop nuclear and produce some more coal-fired power plants. Security, big deal when you have data. Privacy issues. Pricing mechanism, market structures have to be created to be able to accommodate that. New business models, regulatory frameworks, and whether people will accept it or not. So this is a non-trivial problem to solve. It's not just an engineering one. It is, many of these have to be put together. So I call this a tectonic shift. And talking about living 2 miles away from the San Andreas Fault, this is a tectonic shift in the electricity, in the traditional Tesla Edison electricity ecosystem. And what you really want are some holistic, systems-focused solutions that are needed for this. And when I say system, it's not just the engineering system, it's the system of systems that have to be considered all together. So what are the options we have? How can we minimize? So let's take this high penetration of renewables, 50% penetration renewables. How can we minimize the cost? As I said, the cost of electricity generation is quite low. It is only 3 cents a kilowatt hour. So you can make it free. Imagine if it's free, and sometimes it's negative pricing, and I can get into that later on. It is not the cost of electricity generation that is important, it's the cost of electricity delivery that is important. And so how do we minimize the cost of integration that delivers the electricity? Well, there are many options, not too many. One is you can build long distance high voltage DC transmission so that you can balance off regions that are uncorrelated in terms of wind or solar, et cetera. And there's there's a very nice paper that came out in Nature Climate Change this year of what is the optimal network. Leave alone political system, what is the optimal network of high voltage DC backbone? So just like we had the transition from the telephone lines to fiber optic, which was a backbone, so could we create a backbone, a high voltage DC transmission on the order of 1.1 megavolts or so in the United States? And forget about the jurisdictional boundaries for a while. Could we do that? If you did that, the cost of integration of renewables is actually quite low. There is no marginal increase in cost if you put 50% renewables into the grid. But there are lots of issues about permitting, licensing, and going over state boundaries, because state to state, you have to get permission from all of them to build these things. It takes time. You can have ramping natural gas generation as well as storage capacity. This is a natural gas ramping facility that people use. This is Stanford campus, by the way. The Stanford campus is run by a heat pump that is run by the electricity from the grid. And these tanks out here, one is a cold tank, cold water, and the other is hot water tank. And the heating is all done by the heat pump. And that storage provides the thermal storage, which is the cheapest way to store any energy, provides the ability to ramp up and down and even provide services to the grid. Or you can have pumped hydro, which is the cheapest, again, $100 a kilowatt hour. You can't get cheaper than that in terms of electricity storage. And of course, you can have battery, which are more expensive. You can have these things for ramping and providing the intermittency balance. And the question is how much, because that costs money. You could do flexible loads. Now you can control the distributed. So distributed energy resource can give you backflow of energy, but they can also be used to provide the ramping. So instead of just the generation following the load could be managed to follow the generation, so that the wind is going up and down, the load can go up and down accordingly, right? Or maybe most likely it's a combination of 1, 2, 3. This is non-trivial if you were to do this on the grid. So what is the key enabler? And I think what Tesla and Edison and the generations after that, and even 10 years ago, we didn't have the benefit of, is information, which is the key enabler. Why? Because you can now electronically, with signals, manage power. And I'm just showing a small power electronics. There are big size power electronic devices that can provide AC to DC, DC to AC conversion, DC to DC, as well as now AC to AC, which is the transformer. Equivalent transformer can be created using solid state power electronics. They can provide other services like phase angle control, volt-var control, et cetera, which have not really been utilized very much. But electronic control of power using signals to control power, very important. These are not passive devices. These are active. Of course, communication and control, these are now well understood, and these devices are cheap. Sensing, this is a phasor measurement unit which goes into our transmission network in the United States. We have about 900 of them. They're producing petabytes of data, and we don't know what to do with the data. People talk about smart grid. We're only collecting data. We haven't done anything with it yet. So it's not that smart. And these are smart meters, and I'll show you some data from the smart meters where the utility is trying to figure out what to do. They really haven't done much. And then, of course, in the computing side, the computing world is partitioning into two kinds. One is centralized distributed network computing, which is what we call cloud. And the other is distributed intelligence, that is network, which we call Internet of Things. But in this case, when you're talking about the grid, this is not just Internet of Things or Fitbit kind of things. This is the Internet of Things that is connected to a network which has to satisfy the laws of physics. So it's much harder than collecting data from Fitbit and telling you things to do. And of course, data science, and this is all the data analytics of handling, stacking up the right kinds of data and analyzing, using statistics to be able to find patterns which are very difficult to find by just human. And then, of course, these are all getting cheaper and better. So this is an infrastructure which is happening. And the question that we are asking is, how do we connect them? And having worked in Google, I can tell you the people in Google are amazing in being able to manage the data and stack it in the right way to be able to query it and find answers that you would not otherwise get. They're very good. They just don't know what questions to answer in the electricity world. And if you go to the electricity world, they're very good at asking the questions, but they don't know how to handle the data. And so we are looking at this from Stanford and SLAC and saying, could we bridge this gap? Because once you do that, the people who have the questions will find new questions to ask that they can't imagine today. Just like we in Google, we start asking questions which 10 years ago we would have probably never asked. And so that's the kind of the play that where a university can play a role in bridging these two communities. So this is, as I said, this is we're starting an initiative called Bits and Watts. And the name is suggestive, of course, but what we're trying to do is to look at the system. There's a power systems, there's a market system, there's a business model, there's a regulation, policy, finance, and institutions. And this is the Tesla Edison grid ecosystem. And if you are to really do this deep decarbonization or integration of distributed energy resources, you got to look at the whole thing and not just one at a time, because you'll probably get nowhere. So this is what we're trying to do in the Bits and Watts, is really to look at it holistically in a system-focused approach in research and education as well, because our education is fairly siloed. And not just in universities, but even people in the industry are very siloed themselves. They need the education to understand. You need regulators to understand where data science is actually going, so they can make the right regulatory policy, not looking at the rear view mirror, but looking ahead. And that is, has to happen. And this is really the interplay between technology, markets, business models, regulation, finance, and policy. That's the initiative that we're just starting to put together. It's going to be launched end of this month with the industry. And these are some of the people. I'm co-leading it with a gentleman called Frank Wolak, who is in the economics department, teaches in the business school, and he teaches market structures. And we are co-leading this thing. He is a MIT alum, David Danielson, some of you may know. He left DOE, he's now out there. He's the interim director. And these are faculty and staff. Abbas El-Gamal is the electrical engineering chair. Ram Rajagopal, civil engineer. He's a former commissioner, utility commissioner, Diane Grunick, in California. And there are many others out here. He's a former Google fellow who is one of the icons in data science. He has left Google and is joining us. He's another MIT alum, Juan Rivas, in power electronics. The people from the business school, like Steve Comello and Stefan Reichelstein, a physicist who understands the grid quite a bit, Stephen Chu, and many others. So you can see that he's from the law school. And so we're putting this team together to really trying to address it as holistically as possible. And of course, many students, postdocs, and some staff out here. And this is in very close collaboration with the industry and the ecosystem. And the ecosystem includes the regulators as well as the market makers, et cetera, in the wholesale market. So I'll tell you very briefly what this is about. The 3 research thrusts, 1 education thrust, and the other role that we are finding more and more is we call Stanford and SLAC a demilitarized zone. There are military battles that are being fought on the political front. And when that battle is in front of a commissioner, which is a very formal process, the game is over. And so what we have been asked to provide a forum that is informal, where the discussions and dialogue can happen within the ecosystem so they can resolve these issues before they even go to a formal hearing. So this is the convening of the ecosystem which a university can play a role, which I think I'm realizing how important that is to the ecosystem as a whole. Very quickly, 3 initial research thrusts. One is the grid has to be looked at as a whole. It cannot be looked at as transmission system planning, distribution system planning, and then because they're all connected anyway. So we have to blur the boundaries and look at it as a whole system, not only on a power system, but a market system altogether. The second thing is that customers are going to be networked and they will control things, or they will give up their control to someone else, like a Nest or a Tesla and others. So connected customers and communities and aggregated communities in terms of load generation, this is very important. So engaging and blurring that boundary between a customer and their devices and connecting them to the grid is equally important as this one. And finally, there's going to be a lot of data. So we need to handle data in the right way. So what we're doing is creating something called a data commons. And the first thing we're doing is we're putting Stanford campus data up here. What is the data commons? When you have petabytes of data, you cannot send this data in Excel spreadsheets to others. It's a lot of effort and a lot of bandwidth required. So what you really need is to keep that in a repository, arrange it in the right way, and bring the tools, the data analytics tools and others, to the data. So the data commons is that we will put up our data and have you look at them with the tools that are available. You bring your data also so that we can look at not only our data but your data. And we collectively look for insights using these tools, and we can develop these tools together and make them public domain. And so this is something that I think is going to be extremely helpful. This has been done for images and others, for data commons, for looking for, identifying dogs, cats, and cars, et cetera. And this has worked extremely well. It's sort of crowdsourcing, but it's beyond crowdsourcing because you bring your data along with you. And I really hope that we are putting our data. If MIT can join this, we can have this data commons across. Google has opened up its cloud space for us, which is worth a lot, frankly. And so they're helping us in this. And we would love to have MIT and other institutions join this and create, on the electricity side, a data commons. And then, as we say that, for example, the data analytics for time series, of course, they're there inside private companies like Google, but it's not public domain. We will develop them and put it out there for others to use. I'll go very quickly through a few projects. This is a project that started way back in 2009 and 10 from ARPA-E funding, done in collaboration with all of the PG&E, State Grid of China, ABB, AutoGrid, which is a startup company, et cetera. And the idea is very simple. Let's take the meter data of homes, and we were able to get them from PG&E, about 200,000 homes, and asked, what is the profile? What is the demand profile? And PG&E assumed that, and in fact, most of the utilities assume that the data follows this pattern, that people get up in the morning, they turn on things, and the load goes up, then they go to work and goes down, they come back home, it goes up and it goes down. It's like the Golden Gate Bridge kind of profile. Okay, and they assume that all homes follow this. We said, okay, let's look at the data. We run it through a fairly straightforward machine learning tool to find out what the patterns, and we found there are 200 patterns. Only 14% of the homes actually follow that. And there are all these. I found my home following this. I call this the grad student profile. They're awake at night, sleeping during the day, right? I don't know why my home was following that. I guess I'm pulling some all-nighters. But this is what happens. And now in California, they're trying to get from a tiered structure, rate structure, to what is called a time of use rate. And time of use rate is going to be following this. So when your demand goes up, because the idea was that when the demand goes up, the rate should go up so that people shift the demand, et cetera. But only 14% follow this, and that's what the pricing is going to be in the retail. Imagine if you apply that pricing to that profile or that profile, completely different answers. And there was no insight on this before, and this is like the tip of the iceberg. And there are thousands of homes that follow that. Maybe there's a flaw in how the home is being operated, and if I want to see whether my home is efficient or not, I ask PG&E. What does PG&E do? It sends a guy to my home to audit my home to figure it out. That's such a 20th century approach. Instead of looking for data common, this data with hundreds of thousands of homes, and see, is there a pattern that I'm seeing, and maybe I can give something actionable to make their home more efficient. That has not happened, and we have not quite done that yet. So this is a simple thing, and this software is open source. Anything that we have decided, anything we do will be open source. This is sitting in PG&E. PG&E is recruiting people to use this software to analyze the data. So this is just one example. This is another project. As you can see, there's some cool acronyms. VADER. This is a project that just started from the Sunshot program in DOE, where we're saying that there's so much of data out there from AMI. These are meters, from micro PMUs. There's a little measurement on the distribution network, SCADA data, PV, the data, EV data, weather data, et cetera. Could we make some sense out of it to provide the situational awareness? These are behind the meter data, but could we provide situational awareness to the utility because they need it? Could we do some operation planning for them? So this is really looking across the meter and can look for value streams. And so that once you create the value stream, people are willing to share the data, because now data sharing is a big deal, big challenge. This is another project. And this is a project that actually started in Google when I was there and now transitioned to Stanford, called PowerNet. It is now funded by RPE with collaboration with Google and the Navy, where imagine if in your home, someone says that, I have to balance the grid. There's so much wind and so many ramps. I really want to shape the load. And then the load shaping, the total aggregate load shaping eventually is broken up in an optimization routine to say, I want this net load from your home. And you figure out how you want to optimize and minimize your costs. So this is like, if you get a signal saying that I want to minimize my cost and I want to produce this net load and it can track it, then I will optimize from all my resources how to meet the net load and actually make some money, because someone's going to pay me to meet the net load. And so this is going on, and of course this is, if there's any cloud connectivity, there's always latency in that. And if there's latency, then you have to optimize it in real time. So you need to have some local intelligence. So how much intelligence you have locally, how much storage of data you have locally, how much you want to put in the cloud, how does latency affect this whole system? These are unknowns. And so this is what we are trying to solve right now. And it's a very interesting project. And of course, in this, there's the customer also. Customer may have preferences. And we are actually constructing a lab to try this out right now. This is the lab. There's a lab in Stanford campus. There's a lab in SLAC, and there'll be labs in the Navy yards. And what we're going to do is to connect them with the cloud. And what we really want to test out is that if there's a pricing, we don't have dynamic pricing, but if you have pricing that is varying, how will the physical system automatically respond to the pricing variations? And will it destabilize the grid? Because the big challenge or at least perceived challenge, is that if the system responds too quickly, it will destabilize the distribution network. Maybe it will. But we want to figure out how to not destabilize it and de-risk it for the regulators to say that maybe this is a good option. So this is a lab that we are, and this, of course, I want to talk about the policy impact. This is part of the convening of the stakeholders to figure out solutions that they would otherwise not develop. Our educational program, this is this is School of Engineering. You can see power systems, power electronic. This is technology trends, electricity markets. There are various law school. There are courses out there. We're trying to figure out in our coursework. We see all this, all these courses all over. Is there a pattern? Can our students take a course and a series of courses from all over to get holistically understand the system of systems? And we're saying if we can do this for our students, maybe the ecosystem also needs it. And we've been talking to the people in the industry, and they all said that's exactly what we need, because they want to level set within the corporation, within the leadership of utilities and other units. Even companies like Siemens and others are saying, engineers do the engineering. They don't always understand the market structures, but the guys who deal with the markets don't quite understand the engineering. And so in this time of turmoil and change, I think it's very important to get this holistic view, and that's hopefully we can do. Anyway, let me stop here. We're going to launch this end of this month with the industry and the ecosystem, and we'll see how that goes. Let me stop here. Thank you very much. I wanted to pose the problem, offer you some solutions, but there's a long way to go in this. Thank you. Yeah.
We'll take some time for a few questions. It was such a clear talk, I think that everybody's. Well, I have a question about the whole idea of integrating the market, the technical part, and the human part, right? I mean, how do you envision the models that you will use for representing all of it?
This is a great question. So I think I was talking with someone. This is where the insights from what has been done at Google is so important. So if you look at a physical system, there are power systems equations you can solve. You got to satisfy Kirchhoff's laws and other constraints that the physical system provides, and you have models to solve it. And you can optimize it. I mean, all these optimal power flow problems, et cetera. These are all there, right? It's very hard to apply those models to human beings. So what does Google do? How do they predict whether you're going to buy shoes from Nike or others? They have a lot of data. They have empirical data. And using data analytics, they have figured out patterns that you will behave like, and they're generally pretty good. And they're getting better and better with more data. It's essentially empirical. There's no models, right? I mean, this is a very interesting. I mean, someone was, and Google was telling me that in the, we go to, I don't know which country it was, the increase in pneumonia and the increase in the consumption of Coca-Cola were about the same. So whenever people drank Coca-Cola, soft drink, the pneumonia went up. Now, of course, one may think that they're correlated. They're not. But there's a proxy for one because the temperature went up. And the temperature went up, the pneumonia cases went up. But the point is that how humans will behave is very hard to predict. And I think that's where data is going to play a big role. Now, what the data people do is they don't have the physical model. So there's an opportunity for hybrids of physical models and data-based, data-driven modeling that will be, I think, very, very critical.
But I think a component of the human behavior is the incentive.
Absolutely.
And so you may have data under normal operation, but then if you create different incentives,
right?
How do you know,
That's right. So people
of what you offer and how people respond to it.
That's right. So people will respond differently, and I think data of how you will respond or I will respond, if you have enough data to collect to the same price changes, you will behave differently than me. And so, but if you have enough data, we should be able to get some understanding of how the whole system will behave. So this is going to be very exciting, I think. Yep.
So I heard the facilities manager from Stanford give a talk this summer, Joe
Steiner. He's
right?
great.
And I thought it might be interesting for people here to hear about what Stanford's doing on its own campus, just hear a little bit more about all of the efforts that have gone into decarbonizing the campus, and because you guys are really pushing kind of campus-led efforts.
Has he spoken out here?
He hasn't spoken here. I heard him out in Colorado.
Okay.
But I thought, the audience might be interested in that.
Yeah, I mean, I think in your energy systems, I mean, he really looked at it from systems point of view, and we used to have a cogen plant, and we got rid of it because it was cheaper and less carbon footprint if you got the electricity from the grid and ran a big thermal storage plants with a heat pump in between. And that turned out to be the best way to operate. And that's what we have right now. And he has not only developed the models, he's actually using that model to operate it. And he's licensing it to Honeywells and others on doing it. So it's a great story. Yeah.
Any other questions there?
Is there any focus on security-related problems?
Oh, thank you for asking. Yes, huge. I didn't even show the data on that. If you look at the reported cases of cyber incidents on the grid, these are only the reported, they are going up exponentially. And it's a very worrisome thing. Getting into SCADA units and controlling them, this is being attacked on a regular basis. So providing for, and cybersecurity is a system level issue. And you can't just, and the more distributed energy resources you have, the more open you are to this threat. So, and it has to be done in what is the whole surface of cyber threats? What are the different vectors that can come in and plan accordingly? And I don't think we have done that for the grid properly yet. At least I'm not aware. Maybe there are people who have done it. But looking at it as a system is what is. So we have some things about it I didn't talk about, but that's an issue that we are grappling with. We don't have a good way to approach it yet. I would also say that it's not just a cyber thing, it's a cyber physical thing. I don't know how many of you know about this incident that happened in San Jose, which is a few, tens of miles south of us, where in the middle of the night they went and shot all the transformers, the substation transformers, into the cooling oil, and they leaked all of them in the middle of the night, 2 a.m. And before they did that, out of the 13, they knocked down 10 transformers. And before they did that, they cut all the fiber optic and telephone lines so that no one can call 911. And this happened in 2013. 2 weeks ago, it happened in Utah. And if there are places in the country that if you go and attack in a physical way, you can really cause some major harm. So it's a both cyber-physical issue.
So you mentioned the two big trends that are reshaping the power system, decarbonization and the growth of decentralized resources or better control of load and demand. How do you see those two relating to each other? Are they parallel trends that we have to sort of just deal with both of them? Where do they overlap or intersect or support one another? Or are they moving in opposite directions in certain cases?
I think there's a way to have some synergies and to help each other out, so they're actually reinforcing. For example, if you have distributed energy resources, the incentives are there, you can use that to control the DERs to be able to accommodate the very volatility in the main, the grid, in the transmission system, in the wholesale market. And so there's a ways to, but the incentives have to be aligned. And then the system has to be designed in such a way to do that so that it doesn't destabilize the distribution network. So there are ways to do it, and that's where we should be going. If you don't pay attention to this, it can go in opposite direction and really destabilize the whole thing, not just the distribution, but the transmission network. And that's the danger that we face if you're not careful.
I've heard a lot of speculation that blockchain will be an important tool in transmitting energy data. Do you see that as part of this evolution towards distributed energy? Do you see a big role for it? Is that
I have to read up on this. I've heard a few times the blockchain. I don't quite understand, so I don't know whether it is viable or not. And but people are saying that, you got to look at blockchain. And I don't know if there's a paper on blockchain or not. I'm sure there are. I can Google it. Yeah.
So, but maybe I think the last question. What is, from your work in Washington and looking at the policy making and so forth, how does this problem look 10 years down the line, 15 years down the line?
Well, there are multiple things. One is that we definitely need a carbon price. If you want to decarbonize and you want to use a market mechanism, which is what the wholesale electricity, and you don't have a price on carbon, it's going to be very hard to decarbonize. We will not decarbonize the right way. Okay, we will decarbonize by, tying your hands behind the back. So that's one thing that has to happen. Second thing is that we need to get high voltage DC transmission permitted and used quickly. And I know that there was one line that has recently been approved after a long time. One high voltage DC transmission between Oklahoma to Arkansas. I don't know if you guys follow. Who follows all that? You guys follow that? And that was applied for in 2010, got approved 2016. 6 years is considered short, but that's only a few hundred miles, like 600, 700 miles. You guys may know this better. But that's it. We need a whole backbone, and we need to figure out how the permitting has to take place quickly, how the arrangements need to be created so that if it crosses multiple state boundaries, is there a tolling system that they get paid for it? We don't have that yet. And so that has to be created, and that's a federal level thing that we bring the states together, but with local decision making. Very important issue, right? Then I think the states have to, whether it's a clean power plan or which is what the Obama approach has been, which is regulatory, but with sharing of resources and advantages between neighboring states, right? So that is, so you can meet your carbon goals. That's available right now. A carbon price will enable you to meet the clean power plan goals really. I mean, people think they're orthogonal, they're actually not. And so if you do that, then how the states actually respond to the pricing mechanisms at the jurisdictional level, at the state level and the local region is very important. For example, I don't know if you know, Texas is a completely different system than California. California is regulated utilities, so I can only deal with PG&E. You go to Texas, and if you're a consumer, if you're home, you can pick from hundreds of choices or tens of choices of companies because it's a deregulated system. And in as I was telling you, in a deregulated system, they can come up with a completely different business model, flat rate, and they'll optimize your, right? The different pricing mechanisms that can be much better for the consumer. But these are jurisdictionally. So how the states respond, I don't know. But I think we need to create some models of excellence of the states that actually is beneficial to the consumer. And that is up for grabs. I don't know exactly how that's going to work out. Does that answer your question?
Okay, well, thank you everyone again.
Okay, thank you. Thanks a lot.